Everyone for coming. It's great to be back in Oxford, and hello to everybody online. I will try and speak as loudly as possible so that everyone can hear what I'm saying. So I'm Josef Boronski. I'm currently an assistant professor at Imperial College London, and I am an inorganic chemist. I will get on to what that means in a bit, but I'm going to be talking about some of our work which, as Saskia says, is revolved around getting metals within molecules to interact with one another and trying to use the knowledge that we gain from these systems to shed more light on the fundamental nature of chemical bonding. So first I will, I'm sorry, but I will briefly just introduce who I am. So I was brought up down here in Medway in the southeast of England, and this is me over in the top left-hand corner. Age 4, clearly an interest in chemistry from an early age, because this is, I think I'm looking at the reaction of sodium bicarbonate and acetic acid there. So that's evidence for my interest in chemistry. I wanted to get away from Medway pretty much as quickly as I could, so I went up to do my undergraduate degree in York, my master's degree, and I then moved over to the University of Manchester to do my PhD. Subsequently, I came down here to Oxford to take up a junior research fellowship. So that's kind of like the sort of first position that allows you to start exploring your own independent research. And since the start of this year, I've been working at Imperial College in my current role. And what does that involve? Well, we're out here in West London, White City. This building here is called the Molecular Sciences Research Hub. It's Imperial's chemistry building. It's a state-of-the-art lab for chemical research, so I spend most of my time here in the lab, supervising students and doing general administrative duties that would require to run the department, and also teaching is a major part of the job as well. So that's kind of what my role entails. But as I say, I am an inorganic chemistry, and what does that mean? Well, we can think of chemistry as really being the central science, sitting between biology and physics on the kind of spectrum. And within chemistry, we can subdivide this into three subdisciplines. So we would have, over on the sort of biological end of the spectrum, we would have organic chemistry, which is concerned with the chemistry of carbon. On the physical end of the spectrum, we would have physical chemistry, which is interested in typically in measurement. And then in the middle, so the central subdiscipline of the central science is inorganic chemistry. So inorganic chemists are interested in all of the elements of the periodic table, pretty much, apart from carbon. So it's a lot of ground to cover. There's a lot of elements to play with. And I'm interested really in uncovering new facets to the personality of each element. In broad strokes, we can sort of compare properties of all of these elements and see how they are analogous to one another, certainly within groups, or perhaps how properties change over the course of a period. But if you dig down far enough, you find the unique properties of each element, and that's what really excites me. And as an inorganic chemist, we've got, if you don't count carbon, we've got 117 elements you could potentially discover new properties of. So there's a lot of ground to cover. So these, on this slide, I've highlighted in blue some of the elements that we've had active research projects looking at. And I'm going to move to another slide now that shows you, that highlights all of the metals of the periodic table. And you see that most of the elements we've worked with have been metals. And actually metals are the majority of the elements of the periodic table. Non-metals are very much in the minority, but they obviously make up some really important, particularly in biological systems, some really important molecules that are important to life. So there's a lot of important chemistry with non-metals, but I'm going to be focusing principally here on the chemistry of all of these elements that are shaded blue. When we come to think about the metals, and particularly their bonding, it can be a little bit perplexing, because we've got these kind of simple models that I'm sure you're all familiar with. We'll just sort of run through those now. So obviously we have over on the left-hand side covalent bonding. We have the sharing of electrons between typically two non-metals. The overlap of their electron clouds forms a covalent bond. This is typically the kind of bonding we find in discrete molecules, ones that we can put a formula underneath and identify with a structural formula, for example. That contrasts with typical ionic species. So we're thinking about salts with lattice structures here, and these ionic interactions are electrostatic in nature. They're attractive Coulombic interactions that form between positively charged, typically metal cations, and non-metal anions. And finally, you may have come across this kind of concept of metals or metallic bonding before. So if we have a block of metal, the bonding in this is kind of different from both of these concepts. If you hold a block of metal in your hand, it feels cold. It's good at conducting heat away from you. And that's telling us something actually about the bonding within this block of metal. Typically what happens is if we have metal, our metals lose their valence electrons to some extent. They lose those, and these electrons then are free to flow and are delocalized through our metallic solid. So they can conduct heat, which is again why they make your hand feel cold when you hold them, but in some cases they can also conduct electricity, for example. But this is perhaps a little bit, obviously this is a very crude drawing here because I've just drawn two lithium atoms. And in a block of metal we've got essentially infinite metal atoms going on and on forever, through which we can delocalize our free electrons. But if we did take two lithium atoms out of our bulk block of lithium metal and try and study them in a molecular system, what would the bonding interaction between these two metal ions or metal atoms look like then? Because at this point, we don't have this sea of metal cations through which to delocalize our electrons, and we don't have the sea of delocalized electrons either. So how are we holding, in these kind of molecular species with metal-metal bonds, how do we hold those metals together? Does it look like a covalent bond? Does it look like this, like metallic bonding, or does it look like something else? And actually the study of metal-metal bonding has consistently redefined how we think about the nature of chemical bonding. I'm going to just highlight some key homo-elemental bonds on this slide. Homo-elemental implies that we've got two of the same thing, so two of the same type of atom bonded to one another. Hetero-elemental would be the opposite, so two different elements bonded to one another. And actually, for all the metals of the periodic table, for the vast majority, metal-metal bonds are known. And I'm going to just highlight some of the really important landmark examples that kind of have changed our thinking. Firstly, we've got over on the left-hand side this species here with a magnesium-magnesium bond. So this is a representative from, I can't see my laser pointer, from these first couple of columns of the periodic table, groups 1 and 2, we call the S block. And this is a molecule here with a magnesium-magnesium bond. This really redefined how we think about the bonding of these metals that typically form very ionic interactions with other atoms. So this was a real landmark species when it was reported in 2007. Then we've got some really fantastic molecules that redefine how we think about the limits of the strongest or perhaps the highest bond orders we can reach. So you might have encountered before this idea of single and double bonding. Most of these elements you may have encountered might form double bonds, for example, and particularly when it comes to carbon, you'll have perhaps encountered alkenes. But here we've got metal-metal bonds with bond orders of up to 5. So this is a chromium-chromium quintuple bond up here. There's 10 electrons shared between those two chromium centers that are bonding them both together. Similarly, we've got this rhenium-rhenium quadruple bond. This was reported in the 1960s and really redefined how we think about metal-metal multiple bonding. So these are two representatives from this D block of the periodic table that houses the transition metals right in the middle. Then we move over to the P block of the periodic table, which is over on the right-hand side. This is from groups 13 through to 18, so the boron group through to the noble gases. And we've got two molecules here as well that are really interesting. So we've got this distannine, which has got a tin double bond. And tin is in the same group as carbon, for example. We know carbon can form carbon-carbon double bonds, form alkenes, for example. And so this is kind of a heavier analogue of an alkene. And then we move on to this dibismuthine, which has a bismuth double bond. Okay, so a couple of things I want to highlight now on this slide. The first thing is that all of these molecules I've highlighted the metal-metal bond, the interesting bit, right at the centre in red. And that's really reactive. That will react with oxygen or moisture or other molecules very, very readily. So the way we stop these metal-metal bonds from decomposing, or these molecules from decomposing, is by appending large, or typically organic groups, so groups made of carbon and hydrogen, appending those to that metal-metal bond to protect it and stop it decomposing. So that's what you can see here in these in black is all the sort of groups that we have that protect our metal-metal bond. Because if, say, two of our chromium-chromium quintuple bonds could bash into each other, they could quite easily turn back into a lump of chromium. So these kind of organic groups are really important for stabilizing these molecules. The other thing that I will address actually at the end of this talk is the fact that this block at the bottom of the periodic table, this is the F block, we don't have any representatives with homo-elemental bonds from this area of the periodic table, but we will sort of describe some advances that we've made in this area at the end. More than just being fundamentally interesting, though, these kind of molecules with metal-metal bonds could be really valuable tools, and that's certainly something that we're hoping to break into with some of our future work. So let me explain what I mean by that. If we think about a block of metal, iron, for example, iron rusts, we all know this. So we have our nice shiny silver metal and it turns orange and goes all flaky and horrible. Understanding that process is quite difficult because the reactions, heterogeneous reactions, as we call them, so reactions that happen in the solid state, are very difficult to study by most of the analytical techniques that chemists have at their disposal. So most of these techniques work in the solution phase. We watch things that are reacting in solution, but actually watching things that happen at a metal surface is very difficult. If we could watch those reactions and understand how we go from a block of iron to a lump of rust, we could, for example, start to think about ways of mitigating against these oxidation processes. And it's not just relevant to rusting or corrosion, it's relevant to all sorts of other, for example, biological processes. If we have toxic metals, as we will come on to in a minute, we can look at the ways these metals oxidize in the body and then perhaps think about ways of countering that if someone is exposed to some of this toxic material. So one thing we can do, if it's difficult to study these things in the solid state, is translate them into molecules. So if we take a lump of metal, take a few atoms out of it, for example, and embed those in a molecule, we can then study this molecular species with all the sorts of solution phase methods that might be at our typically at our disposal. So that's kind of one of the things that we're looking at moving into in the future. Okay, so we're going to start this talk right at the top of the periodic table, and we're going to, towards the end, we're going to move all the way down to the bottom. We're starting up here, right at the top, with beryllium, which is element number 4. It's the second lightest metal. And that lightness means that it has some really, really key properties, key applications. And one of those is in satellites. So beryllium is very light, it's very durable, it's very hard. And that means it's perfect for fabricating things that we want to shoot into space. We don't want to make those out of lead or some kind of really dense metal. So beryllium's perfect for that. It's also used in nuclear reactors. We will perhaps have a little look at this later. So beryllium's, because it's got a very small nucleus, and it's used in moderating rods and control rods in nuclear reactors. If you alloy beryllium with zinc or with nickel or with copper, for example, you can make alloys that are non-sparking. And that might seem like just a trivial little fact, but actually, if you're working with flammable gases, for example, or oils, you don't want tools that are going to cause a spark because you're going to have an explosion. So beryllium alloy tools are used quite widely in those sorts of technologies. It is also, however, extraordinarily toxic. So as a result of this toxicity, beryllium's chemistry is probably the most poorly explored of all the non-radioactive elements. And that's a bit surprising given the position of this element in the periodic table. These light elements, from sort of hydrogen through to neon, from the first and second rows of the periodic table, These form the basis for all of our models of chemical bonding because they're light, they're simple, they're easy to study. And from these models, we can extrapolate and try and explain the reactions that happen in the world around us. So having beryllium as this really glaring gap in our knowledge is a fundamental issue and one that we're sort of attempting to address through our own research. In particular, we're interested in comparing beryllium to some of its neighbours in the periodic table, so particularly hydrogen and boron, and particularly the homo-elemental bonds of these elements. So the HH bond of dihydrogen, H2, has been studied extensively. It's the simplest two-electron covalent bond that you could envisage. So not only is it fundamentally important, but dihydrogen is important to hydrogenation processes, for example, that are important to your margarines. For example, you may have started to study hydrogenation processes that are really important to chemical industry. And similarly, boron-boron bonds are really important because those are molecules with boron-boron bonds are used to fabricate pharmaceuticals, drugs, for example. So not only are these fundamentally important linkages, but they're also industrially relevant. But we were looking to fill in the gap and make the first stable molecule with a beryllium bond. Aside from the fundamental interest in this species, we're also hoping to try and use this to answer some questions of beryllium toxicity. If you get beryllium metal into you, it makes you unwell, but we don't understand the biochemical process that leads to the toxicity. So people have suggested maybe beryllium replaces calcium in proteins or replaces hydrogen in hydrogen bonding networks, but we don't know because the chemistry of beryllium hasn't been developed enough, and that's one of the things we're hoping to look at with these systems with beryllium bonds, understanding how the metal might oxidize, form soluble beryllium compounds in your body that then make you unwell. Okay, finally, just before we get on to some of the chemistry, why is it interesting to work with beryllium from a sort of chemical perspective? It's the smallest of all metal atoms, so most of the rules that work for other metals do not work for beryllium. You can't use the same sorts of principles and processes. You need to really devise new creative strategies. Because it's really small and it's got a high 2+ charge, it loses its 2 valence electrons to make a dication. That means we've got a lot of positive charge in a really small space, because it's such a small atom, and it attracts anything negative to it very, very strongly. And again, this necessitates really creative new approaches that aren't necessarily useful for other metals, but only really work for beryllium. Okay, so we want to make our molecule that has a beryllium bond. And we can sort of think about this process really simply, in theory, as kind of putting a couple of building blocks together to make our molecule. But the problem is the building blocks are really toxic, they're horrible, they react with air, they react with moisture, so we have to find the right conditions and the right reagents to help us put these two blocks together to make our stable molecule with a beryllium bond. Again, I sort of alluded to earlier this idea of these organic groups, bulky groups that are needed to stabilize our metal-metal bonds, and here it's not don't get too worked up about it, but these are just like little rings, C5H5 rings, carbon rings that bond to beryllium, and then these are going to provide some protection to our beryllium bond. Okay, that's all very well in theory, but what does this look like in the lab? Well, as I say, these molecules are reactive towards oxygen and moisture, so we need to handle them under conditions that exclude oxygen and moisture. And so we handle them under inert gases, so things like dinitrogen, N2, or argon. Neither of these gases are going to react with our molecules, so those are appropriate atmospheres to handle them under. And we use glove boxes, and we use what we call Schlenk lines to do this work. So firstly, a glove box. I don't know if you've kind of seen this sort of apparatus before, but basically it's like a big metal tank with a bit of perspex on the front of it, so you can see in, and we can fill that up with our inert gases, so argon or nitrogen. It's got gloves on the front that so we can reach in and manipulate our compounds. So we're going to store them in there in these boxes at the back. We can weigh them out and manipulate them under our inert atmosphere, put them into our reaction vessels. Once our reaction vessels are ready, we're going to take them over here to our Schlenk line. So this is basically got tubes that we can put under either vacuum or under our inert gas. And we've got our reaction vessel down here at the bottom, and we can manipulate our taps of our Schlenk line to help us conduct our reactions and exclude air and moisture. Okay, so that's kind of the principles of how we do this chemistry. But when we've done our reaction, we want to work out whether we've made anything new or the thing that we hope we've made. And one of the first things we do to examine this is NMR, nuclear magnetic resonance spectroscopy. So this is Imperial's NMR suite. It's down in the basement. These are all basically superconducting magnets. They've got large magnetic fields, which is why we've got this yellow and black line here, so that people that have got pacemakers, for example, don't go across the line and their pacemakers stop working. What we do is we have our samples in, these are NMR tubes, they're probably really 0.5 centimetre in diameter. We dissolve our compounds up in those, and then we can put them into our NMR, and we can get a spectrum. I'll sort of, in a minute, I'll outline how that works. But these systems use radio waves, which are really, really long wavelength, to get some information as to the chemical environments in our molecules. Okay, so these are our nuclei in the atoms, in the molecules of our sample that should be dissolved up in solution. Obviously, I haven't done a very good job of dissolving this. You can see there's a lot of solid hanging around here and here. I just thought they were nice colours, but really we'd want to dissolve up that material to get a nice NMR spectrum. But we've got all the atoms in this sample, and they're all arranged, they've all got magnetic moments, and they're all aligned randomly outside of our NMR machine. We put the sample into the NMR, and we then put it into a very, very strong magnetic field. So all of the nuclei that you see in our sample are now aligned with that field. They're all pointing the same direction. Their magnetic moments have aligned with the field. What we then do is irradiate our sample. We give it a pulse of radio waves, and this causes our nuclei to flip their direction. They are then aligned in the opposite direction with the field. As we let them relax, so let them return to their original orientations with respect to the field, they emit energy, and we can detect that energy, and the energy gives us information about what their chemical environment is. So this is a really useful technique. This is what the sort of readout might look like. Usually they're much more complicated than this, but this is a nice simple one for the molecule that we've made. And these lines, which we call resonances, correspond to different chemical environments in our molecule. So this is a really useful piece of evidence to help us work out if we've made what we hope we made. An inorganic chemist's favourite technique, probably, however, is single crystal X-ray diffraction. This is a nice crystal you can see over here that we've made on the right-hand side. It's got a nice red crystal, got big flat faces, and this is what we need for this technique, as the name might suggest. Rather than long wavelength radio waves, in this case we're looking at really, really short wavelength X-rays for this kind of experiment. Here we have Imperial's X-ray crystallography suite over on the left-hand side. I just want to sort of run through how this technique works. So if we think about all of the molecules ranged in a sort of lump of solid material, there's a few ways that they can arrange themselves. They can all stack together in completely random orientations, in which case we would call this an amorphous solid. But if our molecules arrange themselves and aggregate in very ordered ways, so they're all the same orientation with respect to one another, what we end up with is a crystalline solid that has a very predictable and regular pattern, repeats of molecules again and again and again. And we need this kind of repeated structure because when we shoot X-rays through this, it's going to give us some really useful structural information. So our X-rays come into our crystal, and they don't go straight through. They are diffracted. They sort of bounce off electrons within the crystal. So the electrons are obviously associated with the nuclei of atoms or their chemical bonds. And this then gives us some structural information. It tells us where the atoms are in our molecule, but it also tells us what type of atoms those are, because some atoms, they're really big. They're going to be diffracting our X-rays more than little tiny small atoms. So this is really, really powerful technique to tell us about what the nature of the structure of the molecule that we have made is. And so this is single crystal X-ray diffraction data. Once you get all of your diffraction data and you mathematically make sense of it, this is what the molecule that we have made is. So again, we've got these C5H5 rings at the top and the bottom. Don't worry about those, but do worry about the two lime green sort of little tennis balls in the middle. These are our two beryllium atoms, and they're bonded to one another. So now we've got this molecule, we can start to think about what the bonding in it actually looks like. This is the kind of the question I was posing at the start. Does it look like a classical covalent bond? Beryllium is a metal, but it's a very light metal, so it does engage in rather covalent bonding. Or does it look like this kind of a fragment of bulk metal? Again, it's going to be difficult for it to look like that because we haven't got a sea of metal cations to delocalize our electrons through. Actually, it looks like a kind of really unique new hybrid of these two types of bonding. This is a kind of new phenomenon. And one of the ways we can work this out is by harmonizing our single crystal X-ray diffraction measurements with some calculations that we get a supercomputer to do. We get a supercomputer to tell us where the electrons in our molecule are. So that's what you can see over on this side and over here as well. And over on the right-hand side, this is our experimental data. And we have this kind of blue blob on our map here, and this corresponds to a region of electron density with high potential energy, and that's really similar to the electrons that we have in a block of metal. So this is a kind of strange, unusual hybrid of covalent bonding and metallic bonding, but these two metals aren't in a block of metal, they're embedded at the centre of a molecule. So from here, we do hope to sort of use these systems, as I say, to start answering questions about beryllium's toxicity, but we're also using this in other fundamental studies to help reveal more about the properties of some of the other elements of the periodic table. And firstly, I just mainly want to highlight this example that involves nickel. Nickel is a transition metal, centre of the periodic table, and it's used in lots of catalysts. So catalysts speed up chemical reactions, they lower activation energy barriers, and make reactions go more quickly. And these catalysts are used a lot in industry to make, for example, pharmaceuticals, drugs, etc. So they're really, really important. So we need to therefore understand nickel chemistry as well as we can. And before this work, it was believed that nickel could form 4 covalent bonds all at the same time. And through our work here, we've shown that nickel can actually form up to 6 covalent bonds at the same time. So this is really pushing what we know about, this beryllium chemistry is really pushing what we know about the chemistry of other elements of the periodic table. So you can see here, we've got our 6 kind of tennis balls, beryllium atoms bonded to our central nickel atom. Okay, so we come back to this slide again. And I sort of threatened that we might address this block at the bottom of the periodic table, which notably I haven't highlighted any examples of homo-elemental bonds from. This series is actually the F block of the periodic table. Although when we draw out the periodic table, sometimes we put it down at the bottom. In reality, if I can get this laser pointer to work, it slots in here, so this little gap here. And the reason we exile it to the bottom of the periodic table is so that it doesn't become enormously wide and too difficult to fit on the screen. So that's kind of why we display the table like this. But it's actually consists of 2 series of elements. The top row of the F block is the lanthanides, but it's the bottom row that we're going to look at here in this latter part of the talk. And these are actinides. So the actinides are all radioactive metals. They are either nuclear fuel or they are generated in the production of nuclear energy. These are kind of waste products that we form. So they're all really important to society, whether or not we want to acknowledge that. So there's a couple of really notorious members to this series that you might have heard of. So uranium, for example, sits within the actinide series, and so does plutonium. But we're going to look at for the last 10 minutes or so, we're going to look at thorium. So thorium is named after the Norse god of thunder. It's a really unique element. It's got some quite unusual chemical properties. And these are actually, in fact, all of the actinides have unusual chemical properties that are very difficult to predict. And that's because they're so heavy. And I want to sort of briefly address why their chemical properties are so unusual. And this comes to some little bit of basic physics. So if we think about our atom, we've got a nucleus, and going around that we've got electrons. And in a light atom, this isn't really of any consequence. Our electrons happily orbit our nucleus. But as we make our nucleus larger, our electrons have to move more quickly to avoid crashing into the nucleus. So our electrons have a high velocity, and as a result of that high velocity, they gain kinetic energy. They have a higher kinetic energy. So we can see that based on this formula. Kinetic energy is half mass times velocity squared. So these two, if velocity goes up, kinetic energy goes up. This is only really important for heavier elements. The higher mass of our electrons means that they the higher energy of our electrons means that they gain mass. So we can work this out based on Einstein's really famous formula E equals mc squared, in which E equals energy, m is mass, and c is the speed of light. And that's a constant, so we don't need to worry about that. But that means that as energy goes up, mass also goes up. So our electrons with more kinetic energy are heavier. And this has a profound influence on the chemistry of these elements. As the electrons gain mass, some of the electron orbitals shrink, so some of the electrons get closer to the nucleus, some of the electrons get further away from the nucleus, and this therefore has an influence on the chemical bonding of these very, very heavy metals. Aside from the chemical influence of the large size of the nucleus on these elements, it also has a kind of physical impact in the fact that they are radioactive. And I just briefly want to explain how nuclear energy can be generated through fission processes. So this is an example of the nuclear fission process, and we're building it around this uranium-235 nucleus. We can ignore the electrons, these are all nuclear processes. We are going to shoot a neutron into our uranium-235 nucleus, and that means that our mass number goes up from 235 to 236. Our atomic number, our proton number stays the same, but the nucleus of uranium-236 is unstable. So it splits apart into two lighter elements. I've drawn here that as krypton and barium, but in reality this would be a whole range of different combinations of light elements. As it breaks apart, it releases energy, and it also releases more neutrons. And those neutrons can go around and go back to the start over here and propagate that nuclear reaction, generating energy, and that's the basis for the production of nuclear energy. And actually, we use nuclear power at the moment for around 20% of our total energy portfolio, and over the past 60 years, that has led to the generation of billions and billions of tons of radioactive waste. As you see, we're generating lighter elements here through the generation of nuclear power, and we've got to do something with those, because some of those are going to be radioactive, some of those are going to be quite exotic isotopes of elements that have that decay radioactively. So we generate a lot of radioactive waste, and we store the majority of it up here in Sellafield, which is sort of in Cumbria, mainly because it's far away from most people. People aren't going to be exposed to it as readily as if we buried it in the centre of Oxford, for example. This material typically is buried in the ground or stored in big ponds that kind of absorb some of the radiation that it's giving off. And although it is radioactive and we are generating radioactive waste, nuclear fuel is expected to become increasingly important over the coming decades as we try to shift away from fossil fuels to alternative energy sources and eventually entirely renewable energy sources like wind and solar power. And I'll show you a couple of stats that hopefully highlight why nuclear power is a kind of viable option as a halfway house on our way to renewable fuel. So we've got here the amount of the equivalent energy of different amounts of fuel, and a 20-gram uranium fuel pellet. You could hold that in your hand. Uranium isn't too radioactive. It's more the waste, the byproducts that are more reactive of its nuclear fission processes. You could hold a little fuel pellet in your hand, and that would generate the same amount of energy as a ton of coal or nearly 1,000 cubic meters of natural gas. Similarly, we're going to look at emissions now, greenhouse gas emissions, and to make the same amount of energy, a kilowatt hour of energy, Uranium, a nuclear power station, would generate around 1% of the greenhouse gas emissions that a coal or a gas power station would generate. So it is a viable alternative, but again, we've got to think about the effects of radioactive waste, because if we bury that waste in the ground, it's going to enter groundwater, it's going to enter plants and animals, and eventually us, and that's going to cause ecological damage, and it's also going to, if it gets to human beings, it's going to cause health effects, mainly through the fact that these are heavy metals. Their toxicity mainly stems from the fact that they're like lead. They cause damage to your kidneys, for example. Their radiation, particularly of early actinides like uranium and thorium, isn't too much of an issue, but again, their decay products, some of these lighter elements that are formed through their radioactive decay, are very detrimental to human health. Okay, so to cut a long story short, we went through all the steps that I showed you that we did for beryllium, of synthesis and chemical analysis, and we made this molecule, which is the first example of a stable species with actinide bonding. And it's not just a diatomic species, it's not just one atom bonded to another in this case, it's actually a triangle. So we have 3 thorium atoms all bonded to one another. Again, we've got these kind of flanking bulky groups that I've already spoken about a couple of times that protect our core, our metal-metal bonded core. And we're using this to answer some important questions, important fundamental bonding questions. So we've been thinking about the electronic orbitals of these heavy metals and how they overlap. As I say, we need bona fide models and experimental data to really confirm what the chemical properties of these elements are. They're so hard to predict because things like relativity play a big role in their chemistry. So we're looking at the orbitals, the electronic orbitals that these elements use to engage in chemical bonding. And we're also hoping to start using these as models to think about the ways that these actinide elements might oxidize in the environment, and eventually what products might form from that, and how they might therefore enter the environment or enter us, and the damage that can cause. So we've managed to fill in this kind of gap in the F block of the periodic table with another member of this homometallic bonding family. That's kind of where I'll wrap up. I just need to acknowledge that research is always a team effort. We couldn't do any of this, none of us could do any of this on our own, so I just want to thank all of these people who contributed to the work, people who here in Oxford. We've got some really great collaborators over in Germany, and also new colleagues, or colleagues here at Imperial as well. So thanks very much for listening. Happy to take any questions.